this example, we have a population proportion that we would like to estimate. And that means we want the error bound in the proportion instead of the error bound in the mean, which we've talked about previously. And so to find that error bound for the proportion, we're back to using z-scores, and we don't need the t-distribution here when we're dealing with a proportion as compared to a mean. So in this context, we have an election, and we're taking a poll, a survey of 1,200 voters, 65% say the economy is the most important issue. So we want to know what is the confidence interval, the 95% confidence interval for that 65% sample result. And so once we have the error bound for the proportion, we'll do what we have done in the past. We'll add it to the 65%, we'll subtract it from the 65%, and that's our confidence interval. So the key really is, what is the error bound for the proportion? And so we want the appropriate z-score, and in this case it's a 1.96 because we want a 95% confidence interval. So if I go back here a couple slides, I want to show how to use these formulas here in Excel. So if you have a standard normal distribution, you can use these functions in Excel to either find the proportion or find the z-score, depending on what you need in that particular example. And by default, it's giving you left tail probabilities, or it's using left tail probabilities. So let me bring up Excel. Okay, so the first code here equals norm dist. Then what you're putting in is the z-score that you're interested in, and it will output a left tail probability corresponding to that z-score. So let me just do an example, equals norm dist, and I'll put in a value of 0 for the z-score. And then I can choose to put in any mean and a standard deviation if I want. If I'm using the standard normal distribution, this would just be a 0, and the standard deviation would be a 1, and then true, it will give me the cumulative, which is what you want. So I'm keeping all of these things the same. 0, 1, true, that stays the same. And I put in 0 for the z-score, and it should give me 50%, or 0.5 proportion. Now if I make this a bigger value, so let me change it from a 0 to a 1. Now below a z-score of 1, there's 84%. If I change this to a 2, below a z-score of 2, there's almost 98%, and so on. If I make these negative, I can use negative z-scores. So if I do a z-score of -2, I get 0.022, so about 2.3% of the data. So what this function is doing is it's giving me the left tail probability corresponding to a given z-score. For the problems that we're doing here, estimating confidence intervals, we want to invert the process, because what we want to know is what is the correct z-score to give the confidence interval that we want. So we want to specify what this left tail probability is and let Excel then find the appropriate z-score. So let me come back here for a second, because this is a little bit confusing. So we have our confidence level, and then we have this parameter alpha. And the confidence level is really 1 minus this alpha. So if we want a 95% confidence, then confidence level is 0.95, and alpha is 0.05. So if this is 95%, this is 5%. But that 5% is not the left tail probability. The left tail probability will just be half of that, because half of it will be on this side and half of it will be on this side. So when we want a 95% confidence level, we want alpha to be 2.5%, because there will be 2.5% over here and 2.5% over here. I think I might have misspoke there. When we want the confidence level to be 95% and alpha to be 5%, alpha over 2 which gives us the left tail probability, that's going to be 2.5%. So I'll come back to Excel for a second. We want a 95% confidence interval. We want to know what the correct z-score is. Now we do know what the correct z-score is because we've used it before, but I'm just showing you how the calculation works in Excel so that you could do it for any particular confidence level you wanted. We'll do equals norm dot inv for invert, and then we'll put in 0.025 because that will be a left tail probability of 2.5%. And then the mean, we're using the standard normal distribution with a mean of 0 and a standard deviation of 1. And that's it. Close parentheses, hit enter, and it tells me the z-score corresponding to that is negative 1.96. If I round it, it's negative 1.96. Okay, so back to the problem. Now we've specified z, and this is supposed to be a subscript 0.025. I'm trying to keep this the same notation that the book uses. So this means a z corresponding to a left tail probability of 0.025 is 1.96. Now in the confidence interval formulas, we don't use the negative sign here. It doesn't apply. We're thinking about adding and subtracting this this multiple. So we have that value 1.96, and then the standard deviation in the proportion for a proportion is always given by the same formula. So back on the previous slide here, this is going to be true whenever you have a proportion. So we plug in the sample values for the proportion because that's what we have to work with, and the sample size. That gives us the standard error in the proportion. In this case, it works out to 0.014. And then we calculate the error bound for the proportion just like always. This is the correct z-score. Multiply that by the standard error, and that gives us the error bound for the proportion. Add and subtract this from the proportion of the sample, and it gives us this range. So based on the sample of 1200, our 95% confidence interval is 62.3% to 67.7%. So 95% of the samples we would expect to fall in this range. So that is one way we would say this is that we are 95% confident that the true population value is somewhere in this interval.